Good afternoon, everyone. This is lecture 21 of PTRE 475-575, well completions and advanced stimulation techniques. Today we are going to begin module 4, which follows module 3, which was a pretty dense one, I would say. We looked hydraulic fracturing and stimulation in general from several facets, more than just technical, including historical and economic-wise. I saw that everybody submitted the homework, so everything is good in that regard. Your TA will be traveling this week, and then I will be traveling the week after that. And that's basically the lecture that we are losing because of the exam. April, we are losing, I think, April 19 or something. I think the exam is set for, let me just make sure I don't make a mistake here. Okay, let's see. Next week, I'm going to be here. And then April 21, I'm going to be gone to Williston. But I believe that's when the exam is going to be, which is fine because the exam too is going to be, everybody's online, so it's not a problem. I'll just make sure, one second, let me make sure that I have the dates correct. I don't want to say something that is wrong. When it's going to be from exam 2. Exam 2 is next Thursday, April 16th. Okay. So, okay, so it's before, which is fine. We are going to use next Tuesday for a review. And then it's going to be the exam on Thursday. And then April 20th, April 21st, I'm going to record the lecture. If we are behind, I don't think we are very behind. So we are even okay if we skip that. Just if needed, I will record it. But basically, the exam is next. It's like 9 days from today. So let's use. It's basically from where we stopped at slide 21 of module 2 all the way until I will tell you where, until basically where we are gonna make it maybe until where we make it by this Thursday, but I will see about that and let you know. So we have this Thursday for lecture, today for lecture, and then next Tuesday is gonna be review and then exam. And then maybe we don't have a lecture there after that. So basically you have one more homework, one more exam, a term paper, and then the final. Please, if you haven't booked it, if you haven't had a topic confirmed, please do so with me. It's just an email or something, so I can at least direct you towards the right direction. And do remember when you are writing your term paper, one thing is that it's a bottomless task. You can keep refining the language, refining the hypothesis, refining everything, and it will never be like perfect, but it can be excellent if you put enough work to it and keep refining, etc., to make everything. And this is, I think, a practice that I think it should be embedded in your the way you do operate, the way you conduct operations in life in general, as young professionals. That some of you already are, some of you soon are gonna be. Okay. We'll see with the material. We're a little bit ahead of where I would have liked to be. So maybe we can even afford keeping module 4 completely out of the second exam. I will see. And do module 4 is pretty important. And actually, it's going to be easy for some of you because you have seen some of those concepts before. It's a little bit of a review. It just ties everything because we have been talking about stimulations, and stimulations is to help production. So we are going to see, okay, we're going to talk a little bit about production and well performance and all those stuff. Okay, so that was the homework that we will have coming up is not that hard at all. So no big deal about that either. So let's start. The title is Formation Damage and Well Deliverability. And I believe you can see my screen. Okay. So formation damage is a little bit of a catch-all term. It was generalized after it was made. So formation damage is not the best. Is not the more self-descriptive term for the context that we are talking about it in petroleum engineering, because it really talks about near wellbore impediments to fluid flow that basically, prima facie, if you look at the term formation damage, it implies that it makes it hard. Those impediments make it hard for the fluid to flow into the well, okay? But it can work the other way as well. It can work by making it easier for fluid to flow near the well by stimulation. So it's basically the same concept, just different, one for good, one for bad, let's say. But it can also work in the opposite direction. In a way, if it's an injector well and you are injecting, it can be formation damage constraining flow near the well as you are injecting. It suppresses flow away from the well, but it can be also be done the other way, stimulation-wise, helping flow away from the well. Generally speaking, for instance, in Colorado School of Mines that I know, they teach a class. This class is called, or a version of this class is called Formation, Damage, and Stimulation. So basically, they put everything together. Like it's one thing. The concept, the theory is the same. It just can work both directions and also beneficiary and adversely to our operations. The models are pretty simple, and it involves basically changing the permeability in the near wellbore vicinity with respect to the original undisturbed conditions, also known as the virgin permeability, the original permeability of the reservoir, undisturbed. The impacts can be either negative or positive, and the impact of basically the influence well productivity. The more proper, scientifically accurate term is fluid transport alteration. Okay? That's the correct term. But formation damage came earlier and it became a big thing. And everybody's saying formation damage. But for instance, every 2 years, when the year is even, the number is even, like 2026, 2024, 2022, 2028 probably, there is a conference in Louisiana Lafayette by SP called Formation Damage Conference and Exhibition, something like that, or Formation Damage Symposium. And if you go there, I had a student attend it in 2024, where he presented 2 papers. And you will see people from completions, you will see people from stimulations, you will see people from drilling even, you will see people from reservoir, you will see people from production. It's a very, very interdisciplinary kind of theme conference. It's almost as interdisciplinary as ATCE, the annual technical conference and exhibition of SP, which is like the biggest annual event of the Society of Petroleum Engineers, where basically you have every sub-discipline of petroleum engineering presented. And the reason being is that formation damage brings a lot of people together. You drill a well, you damage the near well formation. You complete the well, you damage the near well formation. Sometimes you stimulate the well and you damage the near well formation. Or if you do it right, yes, you improve the near well formation in the similar way that you can damage it if it goes the other way. Then the production people are dealing with this formation damage, and the reservoir people have to model it or include it into their models. So it's a very, it's a uniting theme that everybody cares about formation damage. You know, back in the day, they used to be like, the companies were like configured in a way that it was like reservoir people, reservoir group, talking only to each other. Production people, production group, only talking to each other. Drilling people, only talking to each other, you know? They met like, you know, every Christmas and maybe another couple of days of the year, and everybody was asking each other, oh, how are your kids doing? You know, general questions, like, because they didn't see each other often. Then the industry went to a different kind of model called the asset groups, where you have a group working on a particular task, and then you have a mixture of a lot of disciplines being represented into that group for that particular purpose. It's like an ad hoc kind of configuration. And there is some disadvantages. There are some advantages of using asset groups, but also some disadvantages. For instance, there are some disciplines that are not very well represented within that asset group, maybe because the production engineer was weak and he did not like hold his cup when it comes to the project, and the project was designed poorly on that aspect. Or maybe the asset team leader is also has his own specialty, right? His own sub-discipline, and he sort of imposes that in the way the asset group is working. That's a complaint I heard a lot by people in the industry. It might be called asset group, but they are really working, they are really focusing on what the asset leader, the asset team leader is specializing on very many times. But yeah, formation damage is not like that. Everybody cares about. So it has a position, I would argue, in every applied class in a petroleum engineering curriculum. Okay, so here we see in the picture more or less the way that we're gonna model it at academic level, or more like elementary level, classroom setting. We're gonna simplify the model into two layers: the damage region and the undamaged region. And you're gonna use a different permeability in the damaged region than the undamaged region. And that's how you do the calculations, the equations that you derive, et cetera, for it. And obviously, as if you are dealing with stimulation, you want to make this damaged region permeability very high, so it's a stimulated region permeability. It's very good, it helps flow. That's basically your goal. And if you are not a stimulation guy, any kind of operation you do to the well, you don't want it to damage the well too much. You don't want to bring the damage region permeability lower and lower and lower, and then you have issues. I had my advanced drilling professor had a student back when I was a PhD student or a master student. And this student was using, he complicated the model. He added complexity to the model of formation damage. He made the damage zone into three zones, three different zones for complexity, and was modeling it. It was a girl. She was modeling it different properties in each layer. And it was, you see, everybody cares about formation damage. It can really be detrimental for your well. I promise it can give you big headaches. So common causes and contributors of formation damage. Solid particles from drilling fluids. Many times there is something we use as a loop in the how do you call it, in the when you do the connection in the tool joints, the threads, there is something called dope, pipe dope, that is basically just like WD-40. It basically lubricates the threads so that they can the connection can be made easily, okay? And it helps the roughnecks make the connection. Many times if you cross thread or if you don't make the connection properly, it leads to other different practical headaches, you know? So pipe dope is helping a lot, and it's a disgusting substance. Don't get me wrong, it's a gooey, disgusting substance, but it's needed. The other disgusting thing about this substance is that it basically damages the formation around the well as it's being drilled. It sort of penetrates the nearby formation and plugs pore space, makes it hard for fluid to flow. And I want to say, when I said it's like WD-40, it's still like heavy. It's like, you know, it's like it's a lubricant basically that it can flow through the pathways, the porous pathways, but it can get to places that and plug them, and then fluid cannot flow the other way. That's what I meant, basically. So during drilling, basically, we can damage the well using solid particles. Cuttings can also damage the nearby formation, okay? The cuttings are not gonna stay. Don't forget, we have what we call a mud cake on the sides of the wall, but we also have some very fine cuttings, very small sized cuttings that penetrate through this, they penetrate through the mud cake and they go in the nearby formation, impacting its permeability. Mud filtrate invasion and fines migration, same thing pretty much. Mud can flow out, damage the near wellbore region, and then if you are producing very fast, if your rate out of your well is out of control because you got very excited and you are able to use some very, very high flow rates and the price of oil is high and you want to bang on it as fast as possible, with the very fast oil production, there will be some very small fines, we call them, like small solid rock particles that are moving with the oil. And they can accumulate in the near wellbore region, and basically you have some control issues, or you need some control, or and basically this is manifested in the form of formation damage.
I have a question, Professor.
Yes, sir. Yes, sir.
Is the formation damage we're talking about the effect in inches or feet, or like what is the?
That's a good question. The near wellbore region is as you define it to be. You will see from the equations that we are gonna do is that it's leaving it to you. So you define it, But practically speaking, I would say a few wellbore diameters away from the well, like something like 2 feet, 3 feet. It gets if it's damaged, the damage is bigger the closer you are to the well, most likely. Okay, and then becomes less, 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 and then almost nothing. And stimulation the same way. It gets bigger when you are closer to the well because that's where the fractures are wider. As the width of the fractures becomes smaller and smaller as you go away from the well, then you are it's less and less, and then eventually you become same as the permeability of the surrounding rock formation, the virgin permeability. But yeah, it basically is very, very near the wellbore region. Very, very near the region near the wellbore. 2 feet, 3 feet is quite typical. That's why this lady, I forget her name, she was modeling it. She was using, she was dividing she discretized, as we call it, the damage region into different layers. So she can apply different properties on each layer and see how that impacts fluid flow. But yeah, very near the wellbore, very near the wellbore. So reservoir stimulation is another way you can contribute to formation damage, fracturing, refrac, acidize, and so on, for good or for bad. You can do a hydraulic fracture job that goes wrong. Okay, you actually damage the well instead of fixing it, making it, stimulating it. That's not good, but it's possible. Improve oil recovery, IOR, water flood, enhanced oil recovery attempts can trigger formation damage. I have a student who's gonna defend his PhD later this month, and this is a very good student. His name is Abdel Malek Abbas. He's the one who received the award for the best paper written by people under the age of 35 from SP. His work is on formation damage during enhanced oil recovery. So in carbonate rocks, there is a reservoir between North Dakota, Montana, and South Dakota called the Red River Field. It's a carbonate reservoir, and it's very, very oil wet. From your petrophysics classes or your reservoir classes, you will know that when the reservoir is oil wet, water floods are not favorable because oil is in the smaller pores and water is only in the bigger pores. So if you end up injecting water and your reservoir is oil wet, the water will flush through and won't displace any oil. You will be pumping water, producing water, and the oil will be staying behind. Okay, it will be a drainage situation. So forget about water flood. They started looking at CO2 EOR, but the problem is that the rock is carbonate. So if you inject CO2, it will mix with calcium in the carbonate. It will create some solids like calcium carbonate, dolomite, magnesium oxide, it will create something like 6 or 7 precipitates. Okay, precipitate is actual solid, small solids. So when you are near the wellbore and you are injecting CO2, you get like a lot of dissolution, as it's called. So a lot of the part of the rock has dissolved and became solids, and those solids flew away. Well, not flew away, they were transported away with the flow stream. But as they move further away, they end up being plaqued. They get stuck at a point where they cannot move any further. So they create damage far away from the wellbore, far away from the injection point. So that's a very, very strange but interesting situation where you have stimulation near the wellbore as you are injecting because of the solution, rock basically melting, and then far away from the well, from the injection point, far away from the injection well, you have damage. So it's like you can permeability increases near the well, near the injection point, and decreases further away from the injection point. So this is very, very complicated. So it's like another obstacle that you need to overcome if you are gonna use enhanced oil recovery. And our answer to it, or our suggestion, was that since CO2 EOR would be detrimental, just like water flood, what we suggest is that you replace part of that CO2 with a rich gas like propane or butane or something, which, yes, it's more expensive, but it basically takes away from the CO2, and then it doesn't, you leave less CO2 to make those damages that I just described. But that's a more complex scenario of formation damage. We actually call that, I think his dissertation preliminary title is something like reactive fluid transport controls of CO2 EOR operations in upper Red River field. So it's basically fluid transport alterations because of reactions, chemical reactions taking place in the near wellbore region. So these are stuff that impact the near wellbore region, causes formation damage or stimulation in some case, in the fourth point case. Now, how do we quantify it mathematically? And this is where the mathematics are gonna come into play. There is a concept called the skin effect, which, if you think about it, it makes a lot of sense. Just like the skin is around your bone, imagine skin around the well, okay? And this basically, it impacts the way fluid moves in this near wellbore region, whether it's moving away from the well or closer to the well, for good or for bad. We say the skin effect of this well is so much. Sorry, the skin of this well is so much. Something like it's -2 or it's +20. What does it mean? It means the damage altered zone in the near well vicinity is referred to as the skin information damage analysis. Sometimes it is assumed that flow alteration effects are equivalent in both directions. That's important because you have a well that is used for production and it has this amount of skin. But you may switch it to injection and then they ask you, what is the skin? And you use the same value. Is this true? Not always, not many times actually, but many times they are forced to use that because they don't have any measurements the other way. Sometimes it's a good guess, sometimes it's a bad guess. But it's very rare that a well that I'm producing from has a certain skin of a certain value, and then I'm starting to inject, and it gives me the same skin. Something called hysteresis. It's basically coming in is one value, going away is another value. Damaged or altered zone is assumed to be axially symmetric with the wellbore axis in order to have a specific radius of damage or invasion. That's what Shamel was asking earlier. Basically, he was saying, what is the radius? And I said up to a few feet. And I think it's gonna clear up with homework 4, which you are gonna see some trends. But it can also, the radius could be variable. If I'm at this point on the well, the radius may be 3 feet. If I'm at this point on the well, The radius may be 2 feet, so it might be changing. But for simplicity, in our estimations, in our derivations, we are going to assume it's the same. So many other simplifying assumptions take place. The version we are going to see is like the most simple it can get because it's at classroom level. If you are using research, if you are doing research on this stuff, you are going to have to go more complex. Okay, what we have here is not enough. It's just for classroom level or industry level operations. So this is the model. Well, radius R, and the radius around it RB. Okay, a radius to the well, to the reservoir RB. Remember, RB goes from the center of the well, so very important. You have an axis Z going to the center of the well, and then you have this skin effect, zone 1, as we call it, and zone 2, which is the untouched region, unaffected region, undamaged region, or unstimulated region. And the height of the well is something like H. This is how it looks from above. It's a little bit of a different symbols in this one. It's like RW is the radius of the well. I want to write. Where is the pen? RW is the radius of the well. RA is the altered region. RA. And then RE is the radius of the reservoir. External radius of the reservoir. And then you have PW is the pressure inside the well. And then the pressure changes all the way to something PL at the edge of the damaged region, all the way to PE outside of the well, outside of the reservoir, sorry. The permeability of the undamaged reservoir is KE, external permeability, and the damaged, the altered region is KA. Now, let me tell you something. If I'm injecting, sorry, let's start with producing. If I'm producing, I expect PA to be bigger than PL to be bigger than PW, right? So fluid goes like this, radially all the way to the well. Now, if I go the other way, if I'm injecting, I'm basically going like this. And then I have PW will be bigger than PL, which will be bigger than PE. So it's the other way around. This is how we are going to model this. To be able to model it mathematically, we have to make one very important assumption, and that is, look at the way the rate is Q. Does it change as I move from PE, from RE, sorry, from RE to RA to RW? Does it change? The answer is no. Q stays the same throughout the reservoir, okay? That's important. Another assumption that I'm doing is that there is only radial flow. So the flow is only like this. There is no vertical component of the flow. There is no flow like this or flow like this. It's only straight radially or like, okay, only radial flow. And this is important a lot of if you go to well testing and reservoir simulation, a lot of equations that we see for fluid flow in the reservoirs are what we call hyperbolic partial differential equations. And the reason is because they are assuming radial flow. Okay, it's a simplification that makes them take that form, and those are really solved with something called the Boltzmann transform, which is a very powerful mathematical tool developed in that is applied in petroleum engineering. Like the Boltzmann transform is very, very. A lot of reservoir engineering theories are based on that. Several. Anyway, but that's irrelevant for this lecture. Comparison between the damaged case and the undamaged, unaltered fluid flow conditions. We are going to use something called Darcy's law, which you already know very well, adjusted for permeability alterations. Pressure build-up equations used to quantify the undamaged rock permeability at some distance into the reservoir. So Darcy's law for radial flow, we also assume that the fluid is incompressible. So another simplification. Henry Darcy was a hydrologist. He's considered the father of quantitative hydrology. The reason is that when he was young, not young, he was like 50 years old or something, in the mid 1800s, living in Dijon, France. He was an engineer or a hydrologist for the local municipality, something like that. And he went and like took measurements in 18 fountains, something like 18 fountains, or like no, he had like 18 measurements in total. I don't know if some of them were from the same fountain, but he looked at different fountains in his jurisdiction, let's say, and he did some measurements between the flow rate and the pressure differentials and other stuff. And he came up with an expression, which is basically the pressure differential divided by the density of the fluid flowing is equal to a constant of proportionality alpha times the length of travel times the velocity of the travel square. Okay, and this is what he basically identified. And after some manipulation, it adopted its modern day form that you guys know it from your earlier classes. K, permeability measured in Darcy's, times the cross-sectional area of the flow divided by mu times the pressure gradient, which is the change in pressure, delta P divided by the length of the fluid flow. And then you have negative sign. Do you know why the negative sign is for? It's because fluid flows from high pressure to low pressure. It doesn't go from low pressure to high. It goes the other way. So that's why you have the negative sign, the direction of the fluid flow. Also notice that he published this result in 1856. He died in 1858, so he barely made it. And he was 56. He was 53 years old when he became known, I guess. A father of modern day hydrology. Anything mathematical hydrology, everybody knows Darcy's law. It's like the Pythagoras theorem of petroleum engineers, pretty much. So there is several variations of Darcy's law and corrections. Why corrections? Because there is several assumptions. One of the assumptions is that you want to have what we call Darcy flow which is a very low Reynolds number flow. I think Reynolds number from 1 to 10, which is very, very low. Laminar flow is not enough because laminar flow is less than, is for Reynolds number less than 2200 or something. But Darcy flow is like even less than that. So you want incompressibility, you want other stuff. You don't want chemical interactions, etc., etc. So there is a lot of assumptions behind Darcy's law, honestly. And there is also corrections if some of those assumptions are violated, how you can make it match. A very famous one is the Forsheimer equation of 1901, which basically modifies Darcy's law. It has another term next to it, plus or minus vita q squared or vita squared q, I don't remember. And no, vita q squared. And basically that is for higher fluid flow. The Forsheimer correction 1901. We're not going to do it in this class, but you may know it. Well, let me show you, since you already know Darcy's law. Forsheimer correction. On the equation. Yeah, vita rho v squared. Darcy-Forsheimer equation is the correction of the Forsheimer, and vita is basically the Forsheimer coefficient. So a little bit of adaptation to the equation to make it match the the violation of the assumption that basically Reynolds number is high enough that inertial forces, which is gravity-related forces, become significant compared to viscous forces. So Reynolds number is still, you still have a laminar flow, but you don't have Darcy flow necessarily. Yeah, it's a high velocity, non-Darcy flow. I wouldn't argue that Forsheimer is very, very good with turbulent because you can increase the Reynolds number to a point where Darcy, the Forsheimer is not very useful. In cylindrical coordinates and oil field units, Darcy's law is given by this equation. So there is a conversion factor of 7.07, permeability, the height of the reservoir, viscosity of the fluid flowing, pressure outside of the reservoir, P, external pressure, wellbore pressure, PW, and then a ln, R external radius divided by RW. That's how you calculate Q in basically the K is Darcy, H is feet, mu is centipoise, P and PW are PSI, and the radii RE over RW really is in feet, but could be cancelled because they cancel out. RE over RW really doesn't matter how you give it to it. And the answer is barrels per day. That's one version. Basically, it's the same equation, but cylindrical coordinates. The outer radius, RE, and outer pressure or external pressure, PE, represent the reservoir limits in this case. Using pressure P at the radial distance R, if you let pressure P be between PE and PW, it's a production well, let's say, and R is between RE and RW, So it's anywhere from the external bound of the reservoir or the outer bound to the wellbore. I can adjust this equation so it solves for the unknown. So basically, let me clean. I take the equation, I make mu Q divided by 7.07 kH equals to P minus P, not PW, divided by ln of RE divided by R. Why is the case? Because Q is constant. Okay, if Q wasn't constant, I wouldn't be able to do that. And this translates to P minus P divided by ln of RE, which is going to be a constant minus ln of R. R is the variable. Only P and R are variables here. This is unknown. This is unknown. Known, 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 known. So if I have Q, I can solve for P in terms of R. So let's take this here. I know we said, sorry guys. Today's been a day of one of those days. I always make the same mistake. Known, 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 known. So constant, right? And let's call it C. So C becomes equal to this. So I take the ln RE over RW, multiply by C. By the way, C is a known constant. And then you have P and P. So this is unknown, sorry. This is unknown, and this is unknown. So two unknowns in one equation. It's like having y equals mx plus c. It's just a little bit more complicated. It's a logarithmic relationship, this one. Then I rearrange, and I solve for P equals to P minus C times ln of RE minus ln of R. And then I have P equals P plus C ln of RE over R. Okay? And then if I tell you in the homework, give me P at different R's. You're going to use this equation, let's say, use different R values. It's like doing y equals mx plus c. Okay? But I want to bring something to your attention. Okay? Can I do the same analysis as before here, as I have here? Still, this is C. Okay? I know it. But instead of this, I want to use something else. And instead of this, I want to use something else. And then instead of this, I want to use something else. And instead of this, something else. So I'm going to have C equal to P minus PW divided by ln of RW, sorry, ln of R over RW. Okay? It's the same equation. I just didn't take PE now. I chose PW. PW and PE are what we call boundary conditions. I know the pressure at RE is PE, and I know the pressure at RW is PW. So now it's like when we were at school and we were doing, when we were in like middle school, and they were giving you 2 points, and they say find the slope and the intercept of this line. You find the slope from those 2 points, and then you do y equals that slope times x plus c. And then you need to find c, the y-intercept. So you basically take that one of those 2 points, and you plug them in, and you get c. You can use any of those 2 points, right? You're probably going to be using the one that is easier for you. Same way here. I have 2 points. I have RE, comma PE, and I have RW, PW. Okay? And here I use this to do this. And now I'm using this for this. So P minus PW divided by ln of R over RW, same as P minus PW ln of R minus, what am I doing here? ln of RW. So this is constant, this is constant, this is unknown, this is unknown. And then I can come down here and do the same thing as before, as here, ln C ln of R minus ln of RW, P minus PW, and then I rearrange everything, and I have P equals to C ln of R minus ln of RW. Ah, come on. Plus PW. Okay? And then P is equal to PW plus C ln of R over RW. This should always be bigger. Whatever you have in the ln parenthesis, it should be bigger than 1. R is bigger than RW, so R goes on top. Also notice here that C can be negative or positive. So it doesn't really matter if I have plus here or negative. It's the same thing because C can be a positive constant or a negative constant. That's the beauty of dealing with constants. It doesn't really matter. But those equations, they should give me the same answers. Okay? So in the homework 4, there is 2 ways you can skin the cat in, I think, question 1 or something, or maybe question 2. I haven't posted the homework. I'm not even, but I know what it's gonna be in. And basically it can go both ways. Okay? 2 equations that can give you the same result. If they don't give you the same result, it really means you are making something wrong. But as practitioners in the oil field, I expect that both of those equations can be useful depending on the information that you have. There is a book that I suggested for this class called the Beam Lift Handbook. It looks like an artificial lift book, and it's primarily that, but it has a section on the fundamentals and has a lot of information about those equations. It's a very, very useful book. Written by my old drilling professor, actually, but he has experience. He did like 25 years with his own company after getting a PhD. And he was like, he has a lot of onshore experience. So, yeah, a lot of equations like that in the book. So, this is how it looks like, PE, RE, and we don't see the damage altered region, right? Yet. Because if you see what we did in the previous slide, we only had one permeability. We only care about one permeability. Now I'm going to take these relationships and I will add a second permeability. I will complicate it a little bit more. The flow rate remains constant through the system, hence the pressure drops are additive. So what does it mean? Because Q is constant, the pressures can be added to each other. So you have Q you don't have QE and QA because Q remains constant all throughout. There is no way, no need to designate QE and QA when you are constant. Delta P from the outside of the reservoir until the wellbore pressure is basically delta P. So PE minus PW. And this, if we hypothetically, let's put it here. Okay. Oh, what did I do? Okay, like before. No, let me make it better. All right, we said this is RA, the altered region radius. And we say at the edge of the altered region, we have PA, okay, at the edge here. So the altered region goes from PW at here to PA here. And then the virgin region, the untouched region, undisturbed region, goes from PA to PE, which is here. Same thing. Okay. Look at this equation. It's P minus PA plus PA minus PW, right? So PAs cancel out. I don't really need to know the PAs, right? So it's easy for me. I don't need to know the PAs. It can be anywhere I want, anywhere I set it to be. We are going to take advantage of this in the next slide. We're going to let A, another constant, be mu Q divided by 2 pi KH. The 2 pi is because it's a cylindrical reservoir. Remember, we used to have C equals 7.07. The 2 pi is in that 7.07. Okay, it includes that along with other conversions. Now, A is this. So we have the 2 pi and we have the KH. And then we have something like A times ln of RE minus ln RW divided by K average. All of those are constant equals to ln of RE minus ln of RA divided by KE, the undisturbed permeability of the reservoir, plus A times ln of RA minus ln of RW divided by KA. Okay, those added together. What I'm going after here is that if I set my, if I set my RA at a certain point, and I know my KA, and I suppose that I also know KE and RE, and obviously I know RW. RW is the easiest one. I know the radius of my well. I can use this to solve for this, which is what I input on my calculations or my simulator. So for the average permeability, it's gonna look like this. And basically, this is like averaging in a cylindrical fashion as you move from one layer, cylindrical layer, to the next, to the next, to the next. Obviously, this is 2 layers. You can do it with more layers. You can have KA1 and KA2, making it to RA1 and RA2 respectively. Any one of you knows what kind of average this equation represents? It has a specific name. It's called the harmonic average. Okay, and this is a common question. Like they can ask you, how can you average the permeability of a damaged region for the around near a well? The answer is by taking the harmonic average between the altered permeability, and the unaltered, the undisturbed permeability. So that's an important concept. Just like it's a permeability average weighted based on the smaller permeability plays the biggest role. It's the opposite of the geometric average, where the largest plays the biggest role. Here is the lowest. If you have formation damage, the lowest permeability will play the biggest role in the resultant K average. So you can very easily, if you damage your well, you are impacting your fluid flow to that well very, very progressively because of that harmonic average. It's like when we do the resistance of two parallel circuits, I believe, versus series. I think for one of those configurations, we do the harmonic average. Same thing here. Same thing here. Any questions before I move on? Okay. We have about 10 more minutes. I have a 1:50 o'clock meeting 5 minutes after the class, but I will have to go to the restroom before I go to the meeting. So we'll finish the class on time. So two permeabilities in radial series. As Ka goes to 0, extreme case where you really damage your near wellbore region, the average permeability will also go to 0. And as the radius of this damage permeability region increases, even if it's not 0, the K average will eventually become Ka. It's one of those features of the harmonic average. The smallest permeability dominates this average. So we have a ratio called productivity ratio, which you might have talked about it, I believe, in production. And not to be confused with productivity index, which we'll always also talk about it in this module. But the productivity ratio is more simple, actually. Is the K average divided by K. Okay? The biggest difference, if the reservoir is not damaged, K average would be equals to Ke, so PR would be 1. Okay? But if the permeability, if the reservoir is very damaged, it's gonna go like less than 1, all the way to 0 if you made such a bad job. It will never be 0, 0, but or it can be bigger than 1, and then it's good. So if you are 1 is basically the threshold. You go like less than 1 is damage, bigger than 1 is stimulated. Now you can expand this mathematically, this ratio, and then you have Ka ln of Re over Rw divided by Ke ln of Ra over Rw plus Ka ln of Re over Ra. Mathematically, I think it's very simple. Nothing crazy out of the ordinary, and this is what I described earlier, pretty self-explanatory. You want to be working on a reservoir that has bigger than 1 PR, obviously. And you will hate having to work on a damage zone, actually. In fact, I believe that the best petroleum engineer you become, the best production engineer, or the best completions engineer or stimulations engineer you become, the more likely it is that you will be assigned something with less than 1 because that's where they need your help. So you may be dealing with a lot of those PR less than 1 in your professional life later on. So you may be going home to your significant others or spouses and complain about that reservoir that you are dealing with. Anyway, so how do we quantify the skin factor? We said that the skin is a very good concept to help you understand how formation damage works or formation stimulation. But how do we mathematically quantify it? We talked about permeabilities. We need to talk about put some math in it and talk about skin. How do we convert that, the permeability relationships, to skin? So then damage or altered zone causes an additional pressure drop in comparison to an undamaged well, with the damaged zone usually referred to as skin effect and is quantified. Skin effect is qualitative. It's not number, okay? Skin effect. It's like saying ability to flow. But skin factor is like saying permeability, okay? Like how do you quantify the ability to flow? Very, very similar. So skin factor is what we are going to assign number to, and it's going to be denoted by S, okay? So S bigger than 0 actually means a damaged zone. And S less than 0 means improved zone or stimulated zone. Don't get confused between those. It's a very common source of confusion for young students and even young graduates of petroleum engineering to say, oh, skin factor bigger than 0, positive skin factor means stimulation. No, it means damage. Negative skin factor means stimulation. You'll understand why when you see the mathematics. Hypothetically, skin equal to 0 means no alteration, no damage, nothing. This is how we quantify the skin from the two permeabilities and the two radii. Ke over Ka minus 1 times ln of Ra over Rw. Remember, everything in ln needs to be bigger than 1. Otherwise, ln of 1 is 0, and ln of less than 1 is like error. So if you want a real number for S, you better have something in the ln that is bigger than 1. And how is PR related to skin factor using this equation? PR equals ln of Re over Rw divided by ln of Re over Rw plus S. So ultimately, this is a constant, okay? Let's call this constant R, capital R, okay? Same thing here. So PR is basically R, which is a constant, I don't care what its value is, divided by R plus S. So if S increases, what happens to PR? Let me use a different color. If S increases, PR goes down. That's why positive skin factor means damage, doesn't mean stimulation. If S goes down, becomes negative, PR goes up, stimulation. So if I did a good job in my hydraulic fracture treatment, and I do what I learned about in module 3, I apply them well, I do a careful job, I will have a negative skin, and then a bigger than 1 PR. By the way, it's impossible to have a negative PR. Okay? If you have a negative PR, you need to have a negative permeability. It means that you are applying pressure difference from here to here, like high pressure here, low pressure there, and fluid is moving this way. It's like fluid is moving against it's like swimming against the current. It's impossible. Well, it's possible to swim against the current, but you cannot have negative permeability. That's why that negative sign at the Darcy's law. Anyway, so any questions?
Just question. So the permeability, is it the horizontal permeability or the vertical permeability?
Radial permeability. Radial. Don't think
Radial.
of you're thinking of X, Y, and Z, which is Cartesian. But if we take the Z out and we have just X and Y, and we combine those two to be basically radial. So the fluid flow looks like it's only in the X and Z direction. So let me show you, like here. Look at the Q.
Yes.
The arrows at the Q is basically towards the well, from the edge of the reservoir all the way towards the well, from here to here, from here to here, from here to here, here to here. So it's in the, it's like this is the reservoir, this is the picture on the side view. So the flow is basically like this. But also, like this.
Yes.
Like I'm looking at the arrows from behind as well. So basically like this, radially. There is no Z component, there is X component and Y component, so only horizontal components, as you mentioned earlier. It's common because we have a cylindric, we assume that the reservoir is cylindrical instead of cube. If we are assuming that the cube is the reservoir is something like this, then we'll have to deal with X, Y, and Z. And then I will tell you only X and Y are permeability. Combine those two and get it. Here we have radial. So we don't talk about X, Y, and Z. We talk about radius R, theta, and Z. So only the R is the permeability that we care about.
Yes, Professor. Thank you.
Yeah, if we consider vertical components, so fluid flowing a little bit, it has a vertical component like this. It doesn't flow into the well, but also flows down. So I'm here and I'm trying to go like here. I'm moving like this, but I'm also moving down. So I need to worry about both directions, both permeabilities. In that case, it's a little bit it's more complicated. And actually not this stuff so much, but the stuff that you do in well testing and those like partial differential equations, they become unsolvable. That Boltzmann transform I mentioned earlier in the lecture today is no longer going to be able to come to the rescue. You are going to need more complicated mathematical manipulations to get to the answer. That's why we do this assumption. And also the other assumption is that, which is actually an important one, and is that the thickness of the skin doesn't change as you go up and down the well. Imagine if this was something like this, getting bigger, smaller, bigger, smaller, then it's much more complexity to worry about. then we are assuming that it's just straight, you know, and doesn't change. If it's changing like this, it's not easy. It's not easy mathematically to deal with. Now, if you have a complicated simulator, you can add more complexity and you have computational power. But if you want to do like a nice mathematical model, like analytical model with one equation, it's not easy to do it. You have to take a lot of the complexity out. Okay?
Yes, Professor. Thank you.
Thank you, Shamel. Thank you, Donald. I will see you guys on Thursday. I have office hours tomorrow if anybody has any questions or wants to discuss anything. And I should have the solution key posted very soon since everybody submitted the homework. And thank you for everybody for submitting the homework on time. Very happy with your class. Thank you very much. Have a nice rest of your day.
Thank you.